Okay, welcome to the next class. We'll continue where we left off last time. You may remember what we talked about last time is matrices, linear algebra, and some of the basics. One of the kind of summaries of the last lecture was to see that there are among matrices there's different kinds of groups. In particular, for the class here, of particular interest are the so-called rigid body transformations. That is a transformation of vectors in R3 that represents rotation and translation. So in general, you have the Euclidean transformations, and if R is a rotation, then it's the so-called special Euclidean group, SE3 in 3 dimensions. And so SE3 are typically the transformations that the camera can undergo. You can shift it in space in 3 directions, you can rotate it, and in total there are 6 degrees of freedom. And we'll see a little more closely what these are in the next chapter. But what you see here already is that these groups, these matrices can be represented by groups, and in particular this is by using so-called homogeneous coordinates. That is, the vector x that typically has 3 components is extended by a 4th component, and that is 1. And so you can imagine any point in R3 can be represented by such a vector, the 3 components x, y, z being the coordinates, and then the 4th one being 1. And by using these so-called homogeneous coordinates, the whole transformation can be modeled as a matrix multiplication. So if we multiply this vector by RT01, then it mimics exactly this transformation. And then we can show that these groups are contained in one another, the largest one always being the general linear group, the group that has all invertible matrices. Among these are the orthogonal, the special orthogonal, and similarly by expanding the dimension here, we can embed everything in the general linear group of n+1 dimensions. And then we have the affine transformations, the Euclidean and the special Euclidean, and these are the so-called rigid body motions. Typically, in this case, as in many cases, if things have multiple names, like the special Euclidean group also being called the rigid body transformations, it tells you that it's important, that it plays a role in a number of areas. Then we talked about range of matrices and the kernel of matrices, being the kernel being those that are mapped to 0, the range being those that I can reach by multiplication with the matrix. We talked about the rank of matrices, that is the number of linearly independent rows or columns, and some of the properties. In particular, the fact that the rank and the dimension of the kernel together form the full dimension of space. So in that sense, the kernel and the range of a matrix are kind of complementary. If the kernel is large, a lot of vectors are mapped to 0, it implies that I can only reach a very small subspace in the range. And then we saw some of the properties. I won't review all of them, but one of the important ones is that the rank of a matrix is not affected if I multiply it with invertible matrices. I say here non-singular, that means invertible, it's the same term. Now we come to a topic that is very central in linear algebra in the treatment of matrices, and that is the notion of eigenvalues and eigenvectors. You probably have heard of that as well. Here we, in this case, consider the general case of complex valued matrices, square matrices, and then you can define something called an eigenvector. V is called more specifically a right eigenvector if multiplying by the matrix A does nothing but scale the vector. If that is the case, then this is called an eigenvector. And the reason, something that often when you learn linear algebra in math classes, frequently they don't really tell you what these are used for, what they're good for. But here, what you try to understand by studying eigenvalues and eigenvectors is how the matrix affects space, how it treats a vector, what it does to a vector. And it turns out that in many cases, all the matrix A does to some vector V is scale it. And if it does that to a vector V or any multiple of that vector V, then it's called an eigenvector. And the scaling that it applies, this lambda, is the eigenvalue. And often people don't distinguish right and left eigenvectors, but in principle you should, because it's two different things. Often when people say eigenvector, what they mean is a right eigenvector. But strictly speaking, you could also talk about left eigenvectors, that is a vector V, such that V transpose A is lambda times V transpose. But it's, it's not terribly different in the sense that the left eigenvector V to a matrix A is the same as the right eigenvector to the transpose of the matrix. So there's relations there, obviously. The set of eigenvectors of a matrix is called the spectrum of a matrix. I will use the symbol sigma here to denote the spectrum of the matrix A, the set of eigenvalues. And you can easily compute it in MATLAB again, and this is another, as I said, of the big advantages, that a lot of stuff is already inbuilt in MATLAB. And so if you have a matrix A and a square matrix and you want to know eigenvalues and eigenvectors, you can either call up just eiga, or if you call it up in this way, by assigning it to V and D, then you get the eigenvectors D and the, eigenvalues in the diagonal matrix D, and the eigenvectors being the column of V. That is frequent for MATLAB. For those who have not used MATLAB a lot, you can often call commands directly and they spit out just some information. In this case, it would just give you the eigenvalues. Or if you use the command eig in this assignment, then you also get the eigenvectors in addition to the eigenvalues. Some properties of eigenvectors and eigenvalues. So let's assume that A is a square matrix, any square matrix, n by n matrix, real. Then we have a number of properties. The first one is that if AV equals lambda V for some lambda, in other words, V is some eigenvector of A, a right eigenvector, then there also exists a left eigenvector with the same eigenvalue. So there exists an eta, a vector eta, such that eta transpose A is lambda times eta transpose. And that implies that the spectrum of a matrix A and the spectrum of its transpose are the same, actually. As I said, the left eigenvector of A is the same, is equivalent to the right eigenvector of A transpose. And if for every eigenvalue of A we have a corresponding one for A transpose, this means that the spectrums are the same. The next thing you can show, and again, some of these properties are easy to prove, but for time reasons, I'm not going to go into the proofs here. I just want to give you a compact overview. So some of these properties, again, I will not prove. The eigenvectors of a matrix A associated with different eigenvalues are linearly independent. This is something that you can prove. In addition, you can show that the eigenvalues are the roots of the so-called characteristic polynomial equation. So that is the determinant of lambda times unit matrix minus A equals 0. The roots, that means those values lambda for which this polynomial is 0, they are the eigenvalues. And you can show that the determinant of A is nothing but the product of these eigenvalues. Maybe to show you a little bit where that comes from, we have the eigenvalue equation A times V equals lambda V. And if we rewrite that, put everything on the left side, we get A minus lambda times the unit matrix times V equals 0. And so an eigenvector is a vector V such that this is mapped to 0. Now assume that this matrix is invertible. And you may remember it's invertible if the determinant of this matrix, A minus lambda 1, if the determinant is non-zero, it's invertible. But assume it was 0, so assume the determinant is 0. So assume it's not 0. If that is not 0, then we can conclude that this matrix is invertible. We can apply the inverse, and we immediately get V equals 0. Right? If we apply the inverse of this whole matrix from the left here, then we get V, and on the right-hand side we have 0. In other words, if that determinant is non-zero, then the only solution that you have here is V equals 0. But for eigenvectors, we want some vector that is non-zero. And in other words, we can only get a non-zero vector to solve this equation if that determinant is 0. So this determinant must be 0 in order to have any vector that solves this equation. And this is why you get to the characteristic polynomial. Yes?
The unit vector is an identity. No, the unit matrix.
Yeah. This is, sorry, yeah. So this one that I wrote here is the matrix that just consists of ones in the diagonal. Yes. And so if I take this to the left-hand side, I can rewrite the equation in this one. This I find quite helpful because often I see in exams people will tell me, oh, the eigenvalues are the roots of the characteristic polynomial. And if I ask them why that is, they don't know. And so my recommendation for mathematics in general is don't try to memorize things. Try to understand why they are the way they are, where they come from. And here it's fairly straightforward to get from the eigenvalue equation, which says I want a vector that fulfills the equation, means I want a vector that fulfills this equation. But if the determinant is non-zero, then I only have a 0 vector that fulfills the equation.
May I ask a question?
Yes.
What means if we have determinant lower than 0?
Not lower than non-zero, not equal to 0. And so in other words, if I have a vector that fulfills this equation, then I have to have the determinant must be 0. Otherwise, I don't have a non-zero vector here. And so this is why we get to this equation, and lambda can only be an eigenvalue if it fulfills this equation. And this is if you write out the determinant of this matrix, then you get a polynomial in lambda. And any lambda that fulfills this equation is called an eigenvalue. Next thing, if we have a transformation P that is invertible, so a non-singular matrix P, and we apply it P and P to the -1 from left and right, then we can, then the new matrix, let's call it B, is such that the spectra are the same. So the spectrum of A, the matrix A, and the spectrum of the matrix B are the same. Another thing that you can show. In general, if you have complex problems, so if you have an eigenvalue lambda, some complex lambda that is an eigenvalue, then the conjugate lambda bar is also an eigenvalue. And so if you have a matrix that is real, the spectrum of A is the same as if you take the spectrum and its complex conjugates. Because for every eigenvalue, the complex conjugate is also in the spectrum. Why that is so or why we look into complex numbers here with eigenvalues, maybe to say a little bit about that. We said the eigenvalues are the lambda values that solve this equation. And you might remember, if you have a polynomial and you want to find the roots of the polynomial, in this case it will be a polynomial of order n, because the matrix is n by n. Then there exist at most n roots, n solutions, and in fact if you go to complex numbers there's exactly n solutions. So any polynomial of degree n has n roots, n solutions, if you allow complex numbers as well. And that is why some eigenvalues are going to be real, but in general eigenvalues will be complex. There is a particular setting where the eigenvalue scenario is quite nice, in the sense that you have for a real matrix real eigenvalues. And that is the setting of so-called symmetric matrices. And so this is why we are looking into symmetric matrices. First of all, because the spectrum is very nice, but secondly, that setting actually happens frequently in practice. In a lot of cases in sciences, when you use matrices, for example, you may have heard of the notion of covariance matrices. By construction, a lot of these matrices, like the covariance matrix, are symmetric. And so we can actually exploit properties of symmetric matrices. And as you will see, there are a number of nice properties. Symmetric means the transpose of the matrix is the same as the matrix, meaning if you transpose it, it doesn't affect. And that implies in some sense that right eigenvalues and left eigenvalues, right eigenvectors, left eigenvectors are the same. A symmetric matrix is in addition called positive semi-definite. Sometimes it's called S larger equal to 0, or with this slightly different symbol, if X transpose XS is non-negative. If that expression for any vector X is non-negative, then it's called positive semi-definite. And positive definite if it's strictly larger than 0. So if X transpose S is strictly larger than 0 for any non-zero vector, then it's called positive definite. Now let's assume we have a matrix S square matrix, real square matrix that is symmetric. Then we have the following properties. First of all, one can show that all eigenvalues are real, so that there is a spectrum of n eigenvalues and they're all real. When I say n eigenvalues, a matrix of n by n always has n eigenvalues, but they don't need to be different. There can be multiple eigenvalues that are the same. I mean, the unit matrix has just one eigenvalue, the 1. But if you count them, their multiplicity, one would say it has n eigenvalues, which are all the same. So in general, a square matrix has n eigenvalues, an n by n matrix, and in the case of symmetric matrices, these eigenvalues are all real numbers. In addition, if you have two vectors vi and vj associated with a matrix S that correspond to distinct eigenvalues lambda I and lambda j, then these two eigenvectors are orthogonal. Maybe to show you, I mentioned I'm not going to go into proofs, but the proofs are really not so difficult for a lot of these things. Here, for example, what you can do is you can consider Vi transposed SVJ, so that is a quadratic form, it's called. And then if I assume SVJ is lambda Vj, because Vj is the eigenvalue to the eigenvalue lambda j, then we get lambda j times Vi transpose Vj. If instead I apply the matrix to this vector, I get lambda I times Vi transpose Vj. And if I take both of these equations together, I get lambda I minus lambda j times Vi transpose Vj equals 0. And what I can deduce from that is this is only 0 if either the difference is 0, meaning the two eigenvectors are the same, or the scalar product of these two must be 0. And then you can easily read off if the eigenvectors are not the same, as we assume here, two different eigenvectors, that can only be true if the eigenvalues are not the same, then the eigenvectors have to be orthogonal. And so this is like in 2 lines how you can prove properties such as this one. You can show that there always exists n orthonormal eigenvectors of S which form a basis. So I can use these eigenvectors, I can make them orthonormal, that means orthogonal, and normalized. I can just normalize them to 1. And then I have a basis of space that is spanned by eigenvectors of that matrix. And if you write it in an equation, you can denote these eigenvalues, lambda 1 to lambda n are the eigenvalues of the symmetric matrix S. And then this theorem states that I can diagonalize the matrix. This is what this process is called. I can rewrite the matrix S as V lambda V transposed. And the big lambda here is the matrix that has the eigenvalues on the diagonal, and V transposed are the eigenvectors. And since these are orthonormal, this matrix is an orthogonal matrix. We didn't, I don't think I mentioned that, but orthogonal matrix means, as you may remember, V transposed V is the unit matrix. And if you look at what that means for the columns of the matrix, it means they're orthonormal. On the diagonal, you have the product of each vector with itself, and the off diagonals are the other products, and they're all 0. And so that matrix is an orthogonal matrix. And so this is a diagonalization, because we can transform the matrix S into a diagonal form. And that happens to be useful because once you have it in a diagonal representation, then the action of that matrix on any vector is trivial. It just scales the individual components. In addition, if S is positive semi-definite, if S is positive semi-definite if and only if all eigenvalues are positive or non-negative respectively. And then you can show, let's say we have a matrix S, symmetric matrix, which is positive semi-definite. Lambda 1 and lambda n are the largest and the smallest eigenvalue. Then you can get, then the largest eigenvalue is nothing but the maximum of x times x transposed Sx over the unit circle. If I take all x with length 1, so that is the unit circle or unit sphere in general, and I look what is the maximum of this quadratic form over the unit sphere, it is the first eigenvalue, the largest eigenvalue. Because the eigenvalues, what they do is they scale vectors in that respective direction. And so if I take the unit sphere, it contains all possible directions, and then I look on that sphere what gives me the largest scaling here. And that is the largest eigenvalue. So it's not really surprising. It's rather, I would say, quite intuitive. Similarly, lambda n, the smallest eigenvalue, is the smallest scaling that I can get in any spatial direction. And so I look over all possible directions and look in what direction is that quadratic form minimized. And that gives me the smallest eigenvalue. Once you have a matrix, you can define lengths, norms. Just like we do for vectors, we can do the same for matrices to talk about lengths and then to measure similarity of matrices, for example. And as always with norms, there is no unique solution to how to define the lengths. I mentioned that last time. We can talk about links in a Euclidean setting. We can talk about other kinds of links. And similarly for matrices, I have a lot of freedom of how to choose the lengths of a matrix, the norm of a matrix. One is to look at the action of a matrix on any vector x. And that is, I constrain myself here again to the vectors on the unit sphere. Why? Because if I take all vectors, then that the lengths of that can become arbitrarily large. But if I look at the unit sphere and see what does A do to any vector on the unit sphere, then what I get is another vector, and if I maximize the lengths of that vector, I can define that as a norm of the matrix. And this is called the induced 2 norm. Why is that? Because I take the L2 norm, the Euclidean norm, in the regular vector space. And so I just transfer the definition of the norm of a matrix, often written with 2 bars here, 2 vertical bars. I can just express that by norms on the vector space to which it maps. And that is nothing but, if I write that out, the L2 norm, it's the square root of that vector squared, so x, A transpose AX. An alternative norm is the so-called Frobenius norm that is also encountered frequently in sciences. This is why I mention it here, and we'll see it appear later in class at some point. So that is just, you take all coefficients of the matrix Aij, and you take the square, the summed, and take the square root of it. And you can show that if you this is the same as writing A transpose A, and the trace of that, that means the sum of diagonal elements, and taking the square root of that. It looks a bit strange at the first glance, but if you write out the coefficients of A transpose A and apply and sum the diagonal elements, you will easily see that you get exactly that. In general, these norms are not the same, and you may remember that when you define norms, they're not the same. There's relations among different norms. So if you talk about convergence in analysis, for example, then there's statements that say it doesn't matter which norm you use, that you always have the same notion of convergence. Meaning if one, for example, norm goes to 0, then the other norms tend to also go to 0. But in general, they're not the same, so if you apply this norm or that norm, you will not get the same value out. The matrix A transpose A is symmetric and positive definite. That's interesting. So if I take any non-square matrix, M by N, and it doesn't have to be symmetric, it doesn't even have to be square. Once I do A transpose A, that matrix is by construction symmetric. If you take the transpose of this, it stays the same. And it is by construction positive semi-definite. Why is that? Maybe so I don't lose anyone. A transpose A is positive semi-definite because if I apply X transpose and X on both sides, this is the same as AX squared. And that is, of course, bigger than 0. It's some squared thing. And so this is always non-negative for any X, which means the matrix A transpose A is a positive semi-definite matrix. What it means is once the matrix A transpose A is positive semi-definite, we can diagonalize it and we can write it as V, some orthogonal transformation, and then a diagonal matrix with some non-negative eigenvalues, which I write as sigma 1 squared to sigma n squared times V. And we'll use that rewriting of that kind of matrix later when we come to singular value decomposition. But here we can use it to show what these norms look like when you define them with respect to these so-called singular values, sigma 1 through sigma n, then this induced 2 norm here is just the biggest singular value. And the Frobenius norm is nothing but the sum of the squares of these singular values and the square root of it. And so you see a little bit that these norms are generally not the same, but they are related. In addition to symmetric matrices, we will see in this class so-called skew-symmetric matrices. In German, they're called schiefsymmetrisch, sometimes in English also called anti-symmetric. So these are matrices which are not symmetric, but which are such that if I take their transpose, I get the negative of the matrix. To give you a concrete example, the matrix, say, 1, 1, 2, minus 2, 0, that's a skew-symmetric matrix, one of the simplest that you can think of. So a matrix, if I transpose it, I get the negative.
So that always should be 0?
Yeah, good point. If you have a skew-symmetric matrix, I just forgot that, of course the diagonal has to be 0, otherwise it's not going to work. If A is a real skew-symmetric matrix, then we have several interesting properties which are a little bit related to eigenvalue properties of symmetric matrices, but different. You will see. You remember for symmetric matrices, we had a purely real spectrum. For skew-symmetric matrices, we have a purely imaginary spectrum. That is, all eigenvalues of A are either 0 or purely imaginary, i.e. of the form I times omega, with a real number omega and I being the root of minus 1. So they're purely imaginary. In addition, we have something similar to the eigenvalue decomposition of symmetric matrices, the diagonalization I just showed you. Here we have a similar kind of diagonalization in the sense that I can rewrite any skew-symmetric matrix using an orthogonal transformation V, and then I have a matrix lambda, but in this case lambda is not diagonal, but it is block diagonal of this form, and so I have a matrix that has a lot of 2 by 2 blocks, small 2 by 2 blocks, and then zeros possibly, and the 2 by 2 blocks are skew-symmetric. So these are kind of, and that's as far down in some sense as you can decompose it with an orthogonal transformation. And that means, in contrast to symmetric matrices, I cannot transform it into a space where it is diagonal, but I can transform it into a space which couples only 2 dimensions always, and has a skew matrix acting on that subspace. What that also means, automatically implies, is that the rank of a skew-symmetric matrix is always even. Why? Because any skew-symmetric matrix can be decomposed in a lot of 2 by 2 diagonal matrices, and either these matrices are 0, meaning here these 0, or if they're non-zero, then they always contribute 2 independent dimensions. And so the number of linearly independent rows is always even. Here is a particular example of a skew-symmetric matrix that we will see in the class frequently. It's a 3 by 3 skew-symmetric matrix. And so that matrix, as you pointed out, the diagonal elements must be 0. And the non-diagonal elements, there can only be 3 non-diagonal ones because of the skew symmetry. This one must always be the negative of that one, you can see here. And so we can define for a vector u with the components u1, u2, u3 in R3, we can define an operator called u hat. So u hat is is that skew-symmetric matrix, where I use the values of U1, U2, U3 in this fashion to construct a skew-symmetric matrix. What this obviously shows you is that the space of skew-symmetric matrices, 3 by 3 skew-symmetric matrices, is a three-dimensional space. You have 3 degrees of freedom, U1, U2, U3. This operator mathematically, and this is possibly a bit abstract, but sometimes it's useful to see the structures here. What this operator hat that we define in this way, what it does is it maps from the space R3 to the space of 3 by 3 skew-symmetric matrices. And each vector in R3 is associated with one skew-symmetric matrix. This operator has an interesting property. The matrix U hat is such that if I apply it to a vector V, a three-dimensional vector V, it mimics the cross product. And so you may remember the cross product of vectors in R3. I can represent that as a matrix multiplication if I want. And we'll see later that this is useful. Often the cross product appears in geometric reasonings, but it's a bit nasty to use it, and sometimes it's nicer to just, whenever you see a cross product, we'll do that later in class, we'll just replace it by the operation of a matrix U hat. And the rank of this 3 by 3 matrix is 2. Unless U is 0, of course, then all components is 0. But we just saw earlier, skew-symmetric matrix must have an even rank. If you have a 3 by 3 matrix, the rank can at most be 3. And here it's obviously then if it's even, it's either 0 or 2. Rank 0 means you have a 0 matrix. That's a completely trivial case. And if these coefficients are not all 0, then this is rank 2. And in fact, the vector rank 2 means it doesn't have full rank. Rank 2 means there is exactly one dimension of space that is mapped to 0. And that is, of course, the vector U itself. You may remember if U hat mimics the cross product, so U hat times U is just U cross product with U, and that's 0. And so the vector U is mapped to 0, and that's exactly the kernel of that matrix. Now I come to the last part in this class on linear algebra, and that is the singular value decomposition. Singular value decomposition is very important in many areas of sciences. It is a way to very compactly represent what a matrix does to space. And singular value decomposition allows you to study that action of a matrix, and so you can, for example, when you have, we'll see later, when you have lots of problems in linear algebra, like matrix inversion, like solving linear equation systems, you can study these in terms of singular value analysis. It sounds like something completely new. It's actually not. And the singular value decomposition can be seen as a generalization of the notion of eigenvalues and eigenvectors. Eigenvalues can only be defined for square matrices. And they are real, only assured to be real if the square matrices are symmetric. But what we saw earlier is if you have any non-square rectangular matrix, doesn't have to be square, doesn't have to be positive definite, doesn't have to be symmetric, then the matrix A transpose A is square and symmetric and positive semi-definite. And so, in fact, we can, what the singular values of, basically what we will show in the next slides is that the singular values of the matrix A are essentially related to the eigenvalues of that symmetric matrix. How that is, we'll see in a second. Both the eigenvalue decomposition and the singular value decomposition are used frequently. When I had linear algebra, for some reason, we never had the singular values. I don't know why we skipped them. My suspicion is that from a mathematical point of view, everything is in some sense characterized by the eigenvalues of this matrix. And they're in some sense the same as the singular values. We'll see how that is. Here's the statement beforehand, and for this part, because it is important, I decided to sketch the proof of this statement in the next slides. So the statement is as follows. It's very general. So we have any rectangular matrix, doesn't have to be square, doesn't have to be symmetric, just any matrix, real rectangular matrix. And now we assume that M is larger or equal to N. And we assume that the rank of that matrix, the number of linearly independent rows or columns, is P. Then the statement says there exists a matrix U whose columns are orthonormal, a matrix V whose columns are orthonormal, and a diagonal matrix sigma that has the diagonal element sigma 1 to sigma p, ordered by size, sigma 1 being the largest, sigma p being the smallest, such that A is U sigma V transpose. Now that should remind you of what we just had earlier for symmetric matrices. We had an eigenvalue decomposition where we had U sigma U transposed. What you have here for non-square matrices, for the more general case, is almost the same diagonalization, if you will, except that U and V are two different matrices. They're not necessarily the same. And in that sense, it generalizes the standard eigenvalue decomposition, which is the case if U and V are the same matrix. Here, they're potentially different matrices. But beyond that, you see the structure is the same. The aim is to get some diagonal matrix that models the action of the matrix A. So while the eigenvalue decomposition decomposes a symmetric square matrix with an orthogonal transformation V, A is V lambda V transpose, SVD, the singular value decomposition, decomposes an arbitrary, not necessarily square matrix of rank P with two transformations U and V that are both orthonormal. So the interesting thing is it looks like it's a more general statement, and it is indeed, but the way we prove it is by actually mapping it back to the eigenvalue problem. So here is how that is. Take any non-square matrix, any rectangular matrix A, then A transpose A is square and symmetric and positive semi-definite. And since it is, we can decompose it with non-negative eigenvalues. It's positive semi-definite, so the eigenvalues are also non-negative, and so we can take their, to actually basically use that knowledge that they're non-negative, we use that by writing them as squares of some sigma 1 to sigma n. So these eigenvalues of that matrix are called sigma 1 squared to sigma n squared. And I can write them like that because I know they're positive numbers. And then I have orthonormal vectors, eigenvectors v1 through vn of that symmetric matrix. And these sigma I, so the square roots of these eigenvalues, I call singular values. And this is what I said earlier. The singular values of A are nothing but the square root of the eigenvalues of A transpose A. So this is how I define the singular values. And now what I need to show is exactly this property, that I can rewrite the matrix in this way, where sigma contains on the diagonal these singular values. How do I do that? It's a little bit lengthy, but let me carry you through here. So I have A transpose A. The kernel, so those vectors that are mapped to 0 of this matrix, one can show is the same as the kernel of the matrix A itself. And similarly, one can show that the range of A transpose A is the range of A transpose. Those vectors that I can reach with these matrices are the same. And that means that the range of A transpose, those vectors I can reach with A transpose, is the same as the range of this one, and it's nothing but the span of these eigenvectors V1 through Vp. And the kernel of A is the span of Vp plus 1 through Vn, so that is the vectors that span the remaining space. Once I have the space spanned by the orthonormal the first p eigenvectors with non-zero singular values, then I can span the rest by this space. And now I define vectors ui in the following way. I define them by a times vi scaled by 1 over sigma I. Why I do that we'll see in the following, but basically what I'm constructing here, these u's, are nothing but the columns of this matrix U here. And this is so the proof actually is a constructive proof in the sense that I define sigma I and I define ui such that this equality holds. If I do that, ui is this, then this is equivalent. If I multiply over the sigma I, then I see avj is sigma, avi is sigma I ui. And this expression here is actually essentially what you have in here, in this. So a times v, so a applied to the vector v gives me a scaled version, not of the vector vi, but of the vector ui. Remember, eigenvalues are defined as just scaling of that vector. What I have here is a slight generalization that says if I apply a to a vector vi, it mimics a scaling sigma I applied to a vector ui. And these vectors ui, in addition, are constructed such that they are orthonormal. So if I take the scalar product of ui and uj, and then I plug that definition in here, right? Then I get 1 over sigma I, 1 over sigma j, then avi times avj. And then I can, in that scalar product, rewrite that as vi a transpose avj. And since I know that these vi and vj are orthonormal because they are eigenvectors of that matrix A transpose A, I see by construction that this is either 0, or what I get is sigma I squared. If vi equals vj, then I get delta ij. Delta ij maybe is, if in case you don't know, is this Kronecker delta. Delta ij is defined as 1 if I equals j and 0 else. It's a shorthand notation. Sometimes it's called Kronecker delta. I don't think he got a Nobel Prize for the invention of that symbol, but it's named after him. So, to complete, what we do is we take these vectors ui that we've defined in this manner, and we expand them. These are p vectors from 1 to p. The whole space is larger, so we expand them to a basis of m vectors. That is actually not difficult. We just see what is the remaining space, and we take additional vectors to span that remaining space, and then we can show. We did show already in the previous slide, AVI is sigma I ui, and if we put that all together, then we see that A applied to this set of vectors v1 through vn as columns is the same as the columns of u times that matrix. And so this equation that we saw earlier holds for this subblock of non-zero singular values, but of course if I expand it by zeros, I can easily expand that. Then I have an expression of this form. And this matrix I call V tilde, and this sigma tilde U tilde, and then I have this expression. The tildes are a technicality that I call these the tilde, because strictly what you now still need to do to complete the proof is you simply delete all the columns of U tilde and rows of V tilde, which are multiplied by zero coefficients here. You know, so all these vectors will be multiplied by 0 and the corresponding ones here. And so if we remove these, then we have matrices U, V, and sigma. Sigma being just that subpart here. And then we have that expression A is U sigma V transpose. So that is ends the proof of the singular value decomposition. So what we could show here, I admit it's a bit technical, so what I recommend you do is read over it at home in more detail. Sometimes these more technical things are not obvious to grasp right in class, and sometimes it's useful to sit down at home and look over it again. Yes?
Just about the notation. When you write A times B1,
Mm-hmm.
behind in parentheses. What
Yes.
do you mean? It's a matrix, both column-wise, but
Yes, that's a good question. So what I mean, V1 to Vn are vectors, and so this expression is a matrix indeed, where the columns are V1 to Vn. Yes. That's a good point. Sometimes I don't show all the notation, so it's good that you ask. Sometimes it's better than guessing is to check if that really is the definition. Yeah. In MATLAB, you can do the singular value decomposition easily, so you can write U SV equals SVD of A, and it computes the singular value decomposition. And we will see in a lot of experiments, in a lot of applications, this turns out to be quite handy to have the singular value decomposition here. Here is one more geometric interpretation of what the singular value decomposition, how I can use it to study the action of any matrix A on some vector space. And what we will see, I wrote it in green here, is that if I take any non-square general rectangular matrix A, then it maps the unit sphere into an ellipsoid in a different basis. And how that is, we will see in a second. So let's assume we have oh, sorry, I'm wrong. This holds for square matrices. So this is a study on square matrices, but not necessarily symmetric. So I don't have a complete eigenvalue decomposition, but I still have a singular value decomposition. So let's assume A is some square matrix. Then I have a singular value decomposition U sigma V transposed with orthogonal matrices U and V and a diagonal matrix sigma. More specifically, the columns of U are orthonormal, and of V as well. They form bases of Rn, so n orthonormal vectors. And then let's say a point X in Rn is mapped to a point Y by the transformation A. Then the coordinates of Y in the basis U are related to the coordinates of X in the basis V by that diagonal matrix. So in other words, if I have Y equals AX, the vector X is mapped to some vector Y by the matrix A. I can use the singular value decomposition of that matrix, which I have for any square matrix. So I have Y equals U sigma V transpose X. Then this is an invertible matrix and I can apply U transpose here. It's an orthogonal matrix, so the inverse of U is U transpose, and so I get U transpose Y is sigma times V transpose X. Now remember, in the beginning of the class we talked about basis transformations, that you can represent any point with respect to some basis, but you can also say what are the coordinates of that point in a new basis. And the way we did the basis transformation is by some invertible matrix V or U. So what I have here, V transpose X, are actually the coordinates of a point X in the basis of spanned by the columns of V. So that is the coordinates of X in the basis V, and this is the coordinates of Y in the basis U. And sigma is nothing but the diagonal matrix. And so that means for any square matrix, what it does is basically it is a scaling. If I look at X in the coordinates of one basis and Y in the coordinates of the other basis, then the matrix does nothing but scaling. And that can be formalized a little bit, and this is what I do here. Let's say these coefficients of the point X in basis V, I call them alpha. And the coefficients of Y in the basis U, I call beta. So alpha are the coefficients of X in the basis V, beta the coefficients of Y in the basis U. Then what I have for the points on the circle, so these are points that have the lengths 1, so that is the sum of coefficients squared is 1. That defines a circle. Then the above statement says nothing but that beta I is sigma I times alpha I. So in that basis, expressing the 2 points X and Y in these two bases means that with respect to that basis, the matrix does nothing but the scaling. And more specifically, we say, let's say that these coefficients are on the circle, so we consider points on the circle. Then sum of alpha I squared is 1. If we plug that in here, we see sum of beta I squared over sigma I squared is also 1. And what that means is that if alpha I are the coefficients, alpha are the coefficients of X in one basis, and they lie on a circle, we consider points that lie on the circle, then the transformed points form an ellipsoid. Because this equation, beta I squared over sigma I squared equals 1, the sum of it is the equation describing an ellipsoid. And in this case, it's an ellipsoid that is oriented along the axis of the basis U. So that means what a matrix does to space can be represented as points on a circle, so that would be the points on the unit circle. And what the matrix does, the transformation A, is it creates an ellipsoid out of it in a new basis, where this would be the new basis. So that would be, and yes?
So in this case, why is U invertible in the case that A can be zero?
U is invertible. These matrices are always invertible. That is basically the statement that they're orthonormal.
I mean, U can be square matrix because if you have.
Yes.
And why is that? Is it invertible then?
That's a very good point. I wonder if A has to be invertible for this to hold. I guess not necessarily. I guess then some of these coefficients here may be 0. You're quite right. I suspect for non-zero coefficients sigma I, if they're all non-zero, that only works if the matrix is full rank. I'll check that. So in practice, I think what happens if the matrix is not invertible, then the corresponding coefficients are 0, the diagonal elements. and then it maps some spaces to 0. It means, in the analogy of the ellipsoid, it means that in some dimensions it flattens things completely. So the whole geometric analysis still holds if the matrix is not invertible, if it maps certain things to 0, for example, it still holds, but then the axes basically are flattened. So in some directions it maps everything to 0. The last part about how to use the singular value decomposition is for studying linear equation systems. Something you remember from high school. We have a linear equation system, say AX equals B, and we want to study, are there solutions? And in general, if A is a square matrix, and if it's invertible, then you can apply the inverse, and then you can write X is A to the minus 1 times B. Unfortunately, that strategy does not work if A is not invertible, because you don't have an inverse matrix. And it certainly does not work if A is not even square. If A is rectangular but non-square, you cannot invert it. So the question is, can we still do something like a matrix inversion for matrices that are not square and that are generally not invertible? And it turns out that yes, we can do that. And this is the so-called generalized inverse, sometimes also called Moore-Penrose inverse. And the way we construct it is quite easy. We take the singular value decomposition that we have for any matrix. So for any non-arbitrary rectangular matrix, we have such a decomposition. And then we just invert in the diagonal matrix sigma those elements that are non-zero. And so in some sense, what this matrix does, this is called the Moore-Penrose inverse, a dagger it's often called. And so what you do is you invert just the non-zero diagonal elements. So in some sense what it does is it does an inversion, a matrix inversion, but only in the subspace of non-zero singular values, where I can invert, and the remaining space that is scaled by 0 here is not affected. So loosely speaking, it tries to invert as much of the action of A as is possible in some sense. In MATLAB you have that generalized inverse. It's called P-inverse, P-inf. So if you say X equals P-inf of A, you get this Moore-Penrose inverse. Sometimes it's also called the pseudo-inverse. And it can be applied in many interesting ways. For example, you can show that A dagger A is the same as A. That means it has a similar action as the standard inverse. For example, A times A dagger, once I apply it to A, it doesn't affect A, so it acts like a unit matrix on A. Similarly here, A dagger times A dagger is also A dagger.
How do you pronounce the dagger?
Dagger is, dagger, Dolch in German. Yes, that's why it's called dagger. So now how can we use this pseudo-inverse for equation systems? Let's say we have a linear equation system, AX equals B. And A is a rectangular matrix of rank R that is smaller or equal to M, the minimum of M and N. Remember, the rank of a matrix was the number of linearly independent rows or columns, and so clearly the rank is always smaller than the minimum, smaller or equal to the minimum of the row number or column number. And as you remember from high school mathematics, once you have a linear equation system, you have the three cases. Either you have no solutions, or you have one unique solution, or you have infinitely many solutions. The question is, what do you do once you have no unique solution? Which solution do you take in practice? And this is an important issue because often a guy from applications will give you a specific problem, and then you can possibly realize, oh, the solution is basically the x that solves this equation. But then what do you do when you find out there are infinitely many? Typically it means that the problem wasn't sufficiently specified. Typically it means you need some additional information to figure out which of these infinitely many solutions does the user want. Or if the system has no solution, but the guy who pays you still wants some results. That's an unfortunate case, of course. There is no solution and still you're supposed to present one. Typically the question, then what you can do is you can say, well, maybe I don't get ax equals b, but maybe I can minimize the difference between them in the sense that I can minimize that square. And now the statement is, if you take x equals a dagger b, the pseudo-inverse applied to b, so it's something like inverting the matrix A with the pseudo-inverse, then what you have here, this x min, is the solution that among all minimizers of ax minus b squared is the one with the smallest norm. And that is an interesting result because it means if there are no solutions, then among all that get as close as possible to this solution, I take the one with smallest length. Or if I have infinitely many solutions, then the minimizer gives you 0 here, and still you take among all existing solutions the one with the smallest length. So in many cases, the pseudo-inverse solves all your problems, in the sense that even if you have infinitely many solutions, it finds a unique one, namely the one of smallest length. Or if you have no solution, it finds the one of smallest length that minimizes this residual, if you will. Yes? Why you minimize the lengths here? That's a good question, actually. For example, a lot of these linear equations, the question is what the application area is. And in many cases, the application area would be, for example, that you produce some product and want to sell it on the market and you want to maximize your gain. And then you may have infinitely many strategies that give the same gain. The same revenue, if you will. But then in practice, among these, you may want to have the ones where you have, in some sense, minimum amount of products, you know. If x, for example, is the number of, if, say, the components of the vector x are the number of products I produce of object A, object B, object C, and I'm selling all of these and I want to, you know, maximize the outcome, then possibly I want to maximize the outcome and produce as little as possible. That would be the additional constraint here, that among, so I get the same output but with the least, you know, number of entities produced. But that's a good question. So in practice, that is often an additional useful constraint, that you say, I have a degree of freedom here. I can choose among infinitely many solutions. Which one do I choose? Often the one of minimal norm is a good one, but not always. Not always. That really depends on the application. And so rather than applying black box the pseudo-inverse and saying that's my solution, it's always useful to think, is that really what I want? As you say, do I really want the minimal norm? Maybe I don't want it. Maybe I want some other criterion. But turns out very frequently this is what you want, and then there's a nice solution. So that in general depends on the application. Why does it give the smallest norm? Maybe to give you a little bit of intuition. You see it here. What the pseudo-inverse does, it inverts the action of the matrix in the space where it's invertible, and in the remaining space it maps everything to 0. And so if you apply that to a vector B, it mimics the inverse in that space it's possible, and the remaining space is scaled with 0. And that is why it gives you a very small norm in some sense. That's loosely speaking the reason that this, in the remaining space, it just scales everything with 0. So that's all I wanted to say about linear algebra. I think we still have 15 minutes, so I suggest that we start with the next part. That is this part. So now we got the introduction about linear algebra, about matrices and their properties, etc. And in the end, the singular value decomposition. And now we will talk about more things in the context of multiple view geometry and about how to represent a moving scene. So that is typically the scenario we'll be looking at in this class is a scenario where you have a single camera that moves around an object and takes a number of pictures. Interestingly, a lot of this class will focus on the case that we have 2 pictures, just 2 images. This has been studied extensively, and a lot of mathematical understanding has been gained about the so-called 2-view case. At the same time, one should be honest that real-world applications typically don't have 2 images, but a lot of images. If you take a standard camera today and film, then you get 30 images a second, or maybe even 60 images a second. So actually the 2-image case is a bit of an artificial case there. Nevertheless, it is useful to study the 2-view case because the general case of M views is a little more involved. And so what we do in this class is we start with the 2-view case and then go on to the multiview case, the multiview setting. But before I go on, I want to first mention a little about the historic background here, about the origins of 3D reconstruction, and then I will get to 3D space, rigid body motions, the SO3 group that we had it already, the special Euclidean group as well. So these are rotations, these are rigid body motions, and then we show how with these transformations we can model the motion of a camera. And lastly, I have a part about Euler angles. Some of you may have heard about Euler angles in modeling rotations. It's a slightly different representation of 3D rotations. The origins of 3D reconstruction. So the goal of 3D reconstruction is that you are given a set of views of a 3D object, and you see that same object in multiple views. The assumption is generally, and we will work with this assumption for most of this class, is that the scene I'm looking at is not dynamic, that it doesn't move, it's a static scene. You do know well that the world we live in is not static, and there's a lot of motion and a lot of dynamics. And I should say, to a large extent, the problem of reconstructing dynamic scenes from a moving camera is still a very open challenge. And so typically, to get any useful practical results, you have to constrain the situation. You have to start with assuming things don't move. You have to start with maybe 2 cameras and then go to multiple cameras, etc. Step by step, you can then generalize consider multiple cameras, you can consider moving objects, but for now we will mostly assume a static scene. The reconstruction problem is a classical ill-posed problem. And what that means is there is a more mathematical, technical definition of well-posed problems and ill-posed problems, but here, intuitively, it means that there is no unique solution to the problem I'm looking at. Typically, once I have two images of a scene, you have multiple interpretations that would be consistent with that, with these two views. And so, in general, in the reconstruction, you will need to impose additional assumptions about the scene, because just from the two views you cannot. For example, to give you a very extreme case, if I have two images taken from two cameras and I want to recover the 3D geometry in the world, I may well have two photographs that are pinned to the two cameras, and so they see random things and nothing about really what the scene is. So that would be a case where you have no 3D geometry and you can basically see arbitrary images. The two things that play a role here in understanding how these images are acquired from the 3D scene is, first of all, that the camera does a so-called rigid body motion through space. So from one point to the other, it rotated and it translated. And the second thing is that in the formation of the image, you have a perspective projection. So a 3D point is mapped to some point on the image plane. And in that projection, you lose the distance from the camera. So once you project onto the image plane, the distance is lost. And the major challenge is, in some sense, to recover that distance from the camera. For any point I see, I want to know what is the distance from the camera. If I have that, then I'm done, then I have reconstructed the scene, but that distance is lost in that perspective projection. I should say there are many possible models of projections from cameras with real lenses, very sophisticated models. For this class, we will focus on the perspective projection, and that is the so-called pinhole camera model. Is one of the earliest cameras, is that you just have a little hole in the wall, you have a dark room, and so all the rays from the world go through this hole, and what you get is a perspective projection of the world. The notion of perspective projection goes way back in history, so that was already studied 400 before Christ. Sometimes when you do science and history of science, I find it quite amazing how early certain things were known already. How, for example, way before Christ, people studied this perspective projection. Euclid, for example. It was then studied again very intensely in the Renaissance. Brunelleschi, Alberti, and others in painting, in art. They wanted to make paintings that are as realistic as possible, and maybe you've seen some of them. They're quite impressive. They give you a very realistic impression of distance, of depths, because they modeled this perspective projection. And so in that period they studied what does the mapping onto a plane of the mapping of 3D onto a plane, how can that be modeled, how can that be captured in a painting. And then it was again picked up in the 17th century in the field and later in the 18th century by Desargues, Monge, Gaspard Monge in the study of what's called projective geometry. The first work on multiview reconstruction is actually quite old already, and this is also surprising from an historic point of view, and that is because we only have computers since the 50s or 60s, so reconstructing 3D from images, you would think that maybe started after the computers were invented. It turns out no, people actually studied that problem well before. And one very important paper is the work of Krupa, who studied the two-view case. And what he studied is a sort of a minimal case. Namely, he asked himself, how many points in 3D do I have to see from two images to get a unique reconstruction of the 3D scene? So I'm assuming I have two cameras. I assume they both see the same set of points. I assume I know which point is which, so the correspondence between the points that I see in the two images. And then the question is, can I uniquely reconstruct the scene, the location, the 3D location of these points? And what he showed that indeed, if you have 5 points in a what's called general configuration, then here he showed that if you have two views of 5 points, that this is sufficient to determine both the camera motion and the 3D location of these points up to finitely many solutions. I mentioned the problem is ill-posed. There is generally no unique solution, but it's already good in contrast to linear equation systems where you often have infinitely many solutions. Here you only have a finite number of solutions, possible solutions. And that is a work of 1913, and that work was then extended, and actually the first algorithm for a computer to do 3D reconstruction was proposed in 1981, the first linear algorithm to recover structure and motion from two views. It's based on the epipolar constraint. We will study it. It was proposed by Longet-Higgins in 1981. And that sparked a whole series of research on multiple view geometry, multiple view reconstruction. There's a number of textbooks, Faugeras, Kanatani, Maybank, Wang, that appeared in the 90s and later as well. For example, there is a book by Hartley and Zisserman. It's called Multiple View Geometry. That's a classical book. And then the book I'm using is a more recent one from the 2000s. And you can see after the two-view case that was then studied in following Longet-Higgins, people quickly also looked at three-view cases. Spetsakis, Alimonos, Shashua, 94, Hartley, they looked at the three-view case and developed algorithms that can treat three views. And then further later on, multiple view cases. So you see that in science often you start by simplifying the problem. You start with two images of a few points, then you take three images, and then typically once you understand how things go, you can study the M view case with M images. This problem of reconstructing the location of points in 3D and the motion of the camera is hence in computer vision often called structure and motion, where structure means the 3D location of points in the world and motion is the camera motion. That is the Euclidean the rigid body transformation, rotation and translation. So this is why these problems are often called structure and motion problems. Interestingly, in particular in recent years, the same problem is called visual slam. And I mentioned that already in class. If you have multiple names, it means it's important. This is a very important problem. The term visual slam is more from the robotics community. So while computer vision people traditionally talk about structure and motion, in robotics you typically call this visual slam. SLAM stands for simultaneous localization and mapping, where localization is the camera motion. I want to localize where is my robot or my camera, and mapping means I want to build a map of the world. So the mapping is the structure and the localization is the motion. And traditionally in robotics, For many years, people have been using laser scanners, and there the mapping part is particularly easy because you get the 3D location of points, you just measure it with the laser scanner. But then you want to estimate your own position, and so you have to align different laser scans to figure out how much did you move. Visual SLAM refers to simultaneous localization and mapping using a camera, not using a laser scanner, so this is why this is called Visual SLAM. It's useful that you've heard both expressions, and you will know if people use one or the other term, it typically means they come more from a robotics community or more from a computer vision community. I think at this point I will stop. This is about the history of 3D reconstruction, just a few slides to get you the impression, and next time we will start by modeling camera motion. Thank you.